Vertical and horizontal harmonic oscillators. Many students are comfortable dealing with horizontal mass spring systems, but get confused if the system is oriented vertically. We attempt to overcome this potential hang-up here. With reference to the figure, at location X, how does the net force on M compare to F elastic in the spring? Draw a free body diagram as evidence. At that location right there, the free body diagram would have mg down, there would be a normal force up, and then there would be an elastic force equal to k times x in that direction. And for what we're doing here, I'm just going to use magnitudes for x and for, let's say, acceleration. I hope you'll forgive me for that, but it makes things simpler in terms of the notation, and often we can just look at the situation and the physics that's there, and we can decide, oh, yeah, the acceleration is in this direction or the displacement is in that direction, and it's going to be okay. How does the net force compare to F elastic? Well, they're equal. The net force is numerically equal to k times x. We now take this system and we turn it vertically. K and M are the same as before, but the mass will hang from the spring as shown. Per the figures, in state 1, no mass hangs from the spring, which we assume is massless. In state 2, the mass hangs from the spring at equilibrium. That is, state 2 is how the system would look if M were simply hanging at rest. We see that in state 2, M's weight has extended the spring a distance h. That's shown right there where I'm pointing with my pen. The weight of the mass has stretched the spring this distance h. And state 3 shows M at some particular moment once we've set this thing oscillating up and down vertically. So let's write a Newton's second law for the mass in state 2. In state 2, the free body diagram would have mg acting down, and then k multiplied by what's the stretch there? It's h. And in state 2, we're at equilibrium. So those two are numerically equal. Newton's second law boils down to mg is equal to k times h. How about Newton's second law for state 3? When the mass has now been stretched, let's draw a free body diagram of that situation. When it's been stretched down to there, mg is still acting downward. But now, because it's been stretched, the upward force is bigger than mg. And that's going to be numerically equal to k times how much has it stretched? It's stretched h plus x, like that. So what would Newton's second law look like? It would look like k times the quantity h plus x minus mg, because they point in opposite directions, and that should equal the mass of this object times its acceleration. Letter D, employ the distributive property to part C. All right, let's do that. What would that be? K times h plus k times x minus mg is equal to m times a. Substitute part B into part D. All right, well, what was part B? That was at the top of the page. mg is equal to k times h. Well, if mg is equal to k times h, then in part D, I can say k times h, that's m times g minus m times g. Oh, well, that gives us k times x is equal to the mass times the acceleration. And how does that compare to what we did back in part A? That's exactly the same. See that? The net force is the mass times the acceleration. Those are identical. Check this out. Whether the spring is horizontal or whether it's vertical, the net force is equal to k times the amount of stretch from equilibrium. That's the deal. The net force is equal to k times the amount of stretch from equilibrium. Now, the equilibrium position differs in the case of horizontal versus vertical. In the case of horizontal, there's no stretch in the spring. at equilibrium. In the case of the vertical, there is some stretch. There's that difference. But in terms of the net force on the mass, horizontal or vertical, is equal to K times the amount of stretch from equilibrium. To summarize, whether we have a horizontal or vertical mass spring system, F net on M, when it is a displacement x from equilibrium, is always equal to K times x. However, F elastic in the spring for a horizontal system is equal to K times x. See part A, that's what we did. For a vertical system, it's equal to K times the amount of stretch plus the equilibrium stretch when the mass is hanging at rest. Furthermore, since equilibrium means the location where a system could remain motionless indefinitely without changing, then a horizontal system is in equilibrium with no spring stretch, whereas a vertical system is in equilibrium with some spring stretch. Namely, for our case, we gave it the variable h. And because the elastic force differs, as well as because the equilibrium position differs, similarly will the energies for the two scenarios differ. But the period, the frequency, the angular frequency of the motion will not differ, because those are related only to K and M. As long as K and M are the same for our horizontal and our vertical system, the period won't be affected. Similarly, you can see the amplitude isn't mentioned at all here. Amplitude doesn't affect period, frequency, or angular frequency at all.